Alright, so we're on to section 7, which is our last section in module 3. This really talks more about multiplying radicals, but instead of just single radicals, like square root of 2 times the square root of 3, which we know is the square root of 6, we have these binomial radical expressions, like this one, where you have two things added together, and then a single radical here. Well, really, the rules for radicals have these same ideas as polynomial multiplication. So distributing, foiling, all the things always work as long as you have the same index. So, if I look at this first example, where we have the cubic root of 2 times the cubic root of 4 plus the cubic root of 12, weird numbers, but it's a single thing outside of a parenthesis, so we'll FOIL. So this would just be cubic root of 2 times the cubic root of 4 plus the cubic root of 2 times the cubic root of 12. So if I multiply those together, I'll get the cubic root of 8 plus the cubic root of 24. So now the problem is multiply, but I always want to try to simplify these radicals. Always good to keep them in simplest form. So I'll look at 8, 2 and 4, 2 and 2. So 8 is 3 2's, and since it's a cube root, I'm looking for a group of 3. And so I have 3 2's. So I can rewrite this radical with the 2 on the outside, and since there's nothing else, it's just 2. I'll do the same with 24, 6 and 4, 2 and 2, 3 and 2. So a group of 3 things I have in this case is the 3 2's. So again, we're doing 3 because it's cubic root. So I can put a 2 on the outside, and then on the inside I just have this leftover 3. And I cannot put these together because you can only add like radicals. This is a radical 3, cubic root of 3, and this has no cubic root here. So this would just be our solution. So we distribute and we simplify our radical. Okay, so here's another multiplying problem, but instead of a single and then a binomial, we have basically a binomial. So hopefully this looks very similar to things like this, where we had x plus 2, x plus 7, which we did by FOIL. If you remember, it's the first and the outer and the inner and the last. So we'll do very similar things here. So we'll take 2 times 4, which 2 times 4 is just 8. 2 times square root of 7. Now this is a 2 and this is a root 7, so you just would write it as 2 times the square root of 7. And then the inside you have 4 times 3 radical 7, so the 4 and 3 can multiply. So it's 12 radical 7. And then the last terms, we have 3 radical 7 times radical 7, so that's 3 radical 49. So now we'll try to clean it up. So this is 8. These two are like radicals because they both have radical 7. So 2 plus 12 is 14 radical 7. And this last one, we have the 3 and then radical 49. You can simplify it, but we should know that's a nice even root. That's 7. So this is 8 plus 14 radical 7 plus 21. So again, we have like terms because these are just 8 and 21. They're just numbers. So I can put those together. So I get 29 plus 14 radical 7. Okay, these problems back here are very similar to the ones we just did on the previous page, where we were foiling. It doesn't really look like FOIL, but if you recall from binomials, we did a very similar thing. When you're squaring something like this, really what that means is we should just write it twice. So I wrote the binomial twice, and now I'll FOIL. So we'll go negative 2 times negative 2, which is positive 4. negative 2 times negative 3 radical 6. So there's no radical in this one, so we just multiply the numbers. So it's plus 6 radical 6. These inner terms would be the same thing. So that's plus 6 radical 6. And this last one's going to be the trickiest one. So it's negative 3 and negative 3, which is positive 9. And the square root of 6 and square root of 6 is the square root of 36. So when we simplify, well, this is 4. Again, these are like radicals because they're both radical 6. So that's 12 radical 6. Plus 9 times the square root of 36. You can break it down with a tree, or we should just know that's 6. So this is 4 plus 12 radical 6 plus 54. And 54 and 4 is 58. So there you go. So we just write it twice and same idea. Okay, so the last one on this page, the last multiplying one we'll do, is another square, and it has an x in it. Now this is a very important type of problem in algebra that we will see quite often, where you're squaring a binomial with a radical with a variable inside of it. So very important we kind of know how to FOIL this. So I'll write it twice, and I'll try my FOIL. Now the first one's probably the hardest one. The square root of x plus 1 times the square root of x plus 1. Well, really what this gives us is the square root of x plus 1 squared, because I'm having the same thing twice, so I would just write it as squared under the square root. And in the next step, that will cancel each other out. So our outer terms are 2 times the radical x plus 1. Our inner term is the same. And our outer term is just 2 times 2, which is 4. So this, like we said, the square root of a square cancel out from like the very first section. So that's x plus 1. These two are like radicals, a little more complicated radicals, but they're still x plus 1. So that's 4 radical x plus 1 plus 4. So the only other thing we can really combine are the numbers here. So I could finally write it as x plus 5 plus 4 radical x plus 1. And again, doesn't really matter the order that you put it in. Could the 5 first, the x first, the radical x plus 1 first. Doesn't really matter. So those are some kind of multiplying problems that you could do with radicals. So next we'll try to do some kind of division. Division of radicals doesn't really work how you'd normally think, because it would be very unfriendly to long divide radicals. So we have a little different process to do them. So the process we're going to use to divide radicals is what we call rationalizing the denominator. Okay? And there'll be two ways to do it. There'll be when there's only a single expression in the bottom, and when there's a more complicated expression in the bottom. So rationalizing the denominator, what it actually means is we're trying to write an expression with no radicals in the denominator. You may remember doing rationalization in geometry when you did some trigonometry. Very similar idea in Algebra 2. So it's a very simple process when you have a single radical on the bottom. All we want to do to rationalize it is we're just going to try to multiply top and bottom by a term to make the bottom a perfect root. Okay, so I'll explain what that means. So we're going to try to multiply the top and bottom by something by one number, because you can only multiply the top and bottom by the same. We're going to try to multiply the top and bottom by the same thing, and then we're going to try to simplify, and hopefully it will get rid of the radical in the bottom. So let's look at this first one. We have 1 over the square root of 2. Very famous number from trigonometry, if you remember. So what I want to do is I want to get rid of this radical on the bottom. So I want to multiply by the same thing on the top and bottom. Now if you remember our factor tree, when we factor things out, if it's a square root, I need 2 of the same thing to make it come out perfectly. So what I'll do is, since I have 1, 2 there, I'm going to simply multiply by a square root of 2. And I'll do that on the top and the bottom. The reason this is beneficial, if I multiply the bottoms now, I have square root of 2 times square root of 2, which is square root of 4. And that is now going to be a perfect root. On the top we have 1 times the square root of 2, which is just square root of 2. And you can have a radical on top, you just can't have it on the bottom. So this is going to be radical 2, and then the square root of 4 is of course 2. So we have kind of divided the radicals. We took 1 divided by the square root of 2. If you take 1 divided by the square root of 2, it is the square root of 2 over 2. So rewriting expressions is one powerful thing of this rationalization, but there are also other uses for it. Alright, let's look at another one. So we have 12 over radical 28. Now, what you can do is we could actually simplify radical 28, because I know that one simplifies, just to make our life a little easier. So if I think of 28, that's 4 and 7, that's prime, that's 2 and 2. So when I simplify it, I have one group of 2's, because it's a square root, so I can put a 2 outside and a 7 inside. So I've simplified radical 28. So what the benefit of that is I can rewrite this as 12 over 2 radical 7. Now if you look, what we end up with is we have 12 divided by 2. Now 12 divided by 2 is just numbers, so that just can be simplified to 6 over radical 7. So I didn't do any rationalizing yet, I just basically simplified it down to its simplest form, and I divided those numbers. So now if I want to rationalize, I'll just simply multiply the top and bottom by the square root of 7. Because what that'll yield, the top will be 6 times the square root of 7, and the bottom will be the square root of 49. Oh, but the square root of 49 is 7. Alright, let's look at this one. Very similar. As variables, so that's a new thing. Now if I look at the bottom, radical 5b, there's nothing I can simplify. You can try, but it's just 5 and it's just b. So I'll go right ahead and I'll try to multiply by 5b, so then I have that perfect group of 2. So if I multiply this, the top will give me 5 on the outside, and then radical 5ab. I just wrote a little nicer. And then on the bottom I'll have the 3 on the outside, and then the square root of 25b squared. And if we've done this correctly, this should always be a perfect root, which it is. So the top stays the same, and the bottom, the square root of 25 is 5, and then the square root of b squared, remember, is how many groups of 2 are there in b squared? Well, there's 1. And again, there should never be a radical left on the bottom. So I can multiply, or I do see here there's a 5 on top and bottom, so I can just get rid of that. So this will give me radical 5ab over 3b. Okay, so one more kind of dividing problem that we'll do is when we have a binomial radical expression on the bottom. So instead of just having one thing, we have two things. So you can see, as in this first example, instead of just having radical 5, I have 3 minus radical 5. So I have two things. It's a binomial term. So we have to do these a little differently. To rationalize these, we multiply by using what's called the conjugate. And this is only when you have a binomial radical expression. Now the conjugate, in general, and this is a term we use a lot in math, the conjugate, for example, of a plus b is a minus b. Those are conjugates because they're the same thing, just with a different sign in the middle. So if I have something like 7 plus radical 3, the conjugate would be 7 minus radical 3. So we actually use this to rationalize binomial denominators. So let's look at a couple examples of this. So I know this is a binomial because it's got the 3 minus radical 5. So to rationalize this, I'm going to multiply the top and bottom by the conjugate. And the conjugate is 3 plus radical 5. And again, you can see it's the same terms, just with a different sign in the middle. Now the tricky about this is now we have 2 times 3 plus radical 5. And on the bottom we have 3 minus radical 5, 3 plus radical 5. So we have to do some multiplying. So this goes back to our first couple pages of these notes. So the top I'll distribute the 2. So 2 times 3 is 6. 2 times radical 5 is 2 radical 5. That one's not too bad. The bottom here I'll have to FOIL. So 3 times 3 is 9. And hopefully I'll eventually get rid of all the roots because I don't want any radicals on the bottom. 3 times square root of 5 is 3 square root of 5. The inside ones are 3 times negative radical 5, so that's minus 3 radical 5. And then minus radical 5 times minus, or positive radical 5 is minus radical 25. But you can see these terms cancel because they're a positive and negative. So this is 6 plus 2 radical 5. Now the bottom here I get 9 minus 5 because the square root of 25 is 5. So this is 4. Now this is a fine answer. But what we're going to try to do, because in our next chapter we'll start simplifying things like this a lot, is if I look at the numbers here, every number that's not in the radical, so the 6, the 2, and the 4, if those all divide by the same thing, we can divide it out. And since those all divide by 2, I can divide the 6 by 2 and get 3. I can divide the 2 by 2 and get 1. The radical 5 is not included. And 4 divided by 2 is 2. So this is a better answer. They're both fine for this section especially, but these are actually both equivalent answers. It's the same as like a half and 2/4. Same thing, just a different way to write it. Okay, let's look at one more example. So here we have two binomials. We have a binomial on top and a binomial on bottom. So when I multiply, I'm going to take the conjugate of always the bottom. So I'm going to multiply by 6 times 6 plus square root of 2. Or 6 plus radical 2. So a very similar idea. We'll just have to FOIL twice. So on this first one, 3 times 6 is 18. 3 times radical 2 is 3 radical 2. 6 times radical 2 is 6 radical 2. And radical 2 times radical 2 is radical 4. And we'll clean all that up here in a bit. The bottom we get 6 times 6, which is 36. 6 times root 2, which is plus 6 root 2. 6 times negative root 2 is negative 6 root 2. And you got to be very careful. There's a lot of terms going on here. Negative radical 2 times positive radical 2 is negative radical 4. So I do know that these are both 2 because they're square root of 4. So when I do my combining, I have 18 plus 2 on the top, which is 20. And then I have 3 radical 2 and 6 radical 2, which is 9 radical 2. And on the bottom, these cancel. So I have 36 minus 2, which is 34. And I can stop there because if you look at this, there is no number that would go into 20. Whoops, wrong way. There's no number that would go into 29 and 34. So you can't simplify it. This would just be as far as you could go. Alright, so that's the end of 3.7 notes. Please go ahead and try the assignment on 3.7, and please ask any questions that you may have. Watch this video as many times as you need.